So, in yesterday's class, we started with the concept of angle of contact, right? Let's just revise certain basics, then we will go to the next part. So, what does angle of contact mean? It is the angle between the surface of the liquid and I'll show you. So, it is the angle between the surface of the liquid, see, the surface of the liquid, the tangent drawn to the surface of the liquid and the container, right? And the container which is internal to the surface is what is called as angle of contact. And we saw some important points related to angle of contact. What is it? It depends on, so angle of contact can either be acute, obtuse, or 90 degrees, depending on whether the adhesive force is greater than the cohesive or the vice versa. So if the adhesive force is greater than the cohesive force, then the concave meniscus is being formed. So concave meniscus means when you see from the top, it appears in the shape of a concave. So at that time, you will have acute angle. Similarly, if the adhesive force is less than the cohesive force, then what will happen? It will be, if the adhesive force is less than the cohesive force, then it will have a convex meniscus. Means the angle of contact will be obtuse, right? If the adhesive force is equal to the cohesive force, then we call it as, then the angle of contact is going to be 90 degrees. So how is it defined? It is defined as the angle between tangent to the liquid surface at the point of contact and the solid surface inside the liquid. So you should not take the solid surface outside the liquid. If you take like this, for example, if you take it like this, you can ask me why not this is theta. No, this is not the angle of contact. So the angle of contact is always measured between the tangent drawn to the liquid surface where at the point of contact and the surface of the container which is interior to the, and the solid surface which is interior to the liquid, that is which contains the liquid in it. So that's what we call it as angle of contact. I hope it is clear, guys. Okay, so you can get a question like this: what are all the values on which angle of contact depends? What are all the factors on which the angle of contact depends on? It is nature of the liquid and the liquid in contact. Okay, second, cleanliness of the surface in contact, because if the surface is not clean, then we can say the water molecules will get attracted to the dirt particles as well. Okay, that time whatever angle of contact you're going to measure will not be accurate. So it depends on the cleanliness of the surface. Third is it depends on the medium above the free surface. So it depends on the medium also. If it is air, it depends. So the medium above it will decide how much pressure it is supposed to apply on the liquid, right? So that will also control the concavity or convexity of this particular surface. So it also depends on the medium and the temperature of the liquid. So these are the 4 points on which, 4 factors on which the angle of contact depends on. Okay. So now we will see how to define the shape of meniscus in a narrow tube. So shape of liquid meniscus in a narrow tube. Okay. So here we are going to see some mathematical details. I will suggest you to concentrate more. Okay. So if you take a molecule O, if you consider a molecule O on the surface of the liquid, which is also in contact with the solid wall of the vessels, then there are various forces that are acting on this molecule O. Are you able to see the arrow marks? See, there are certain arrow marks. Force 1, 2, 3, and 4. Okay, there are 4 forces acting on those particles, on that particle O. What are the names of those 4 forces? One is sigma SV. Instead of sigma, if you're comfortable with P, T, I will write TSV. Then TSL, then TLV and FA. Let me name what they are. One is, so here S stands for solid. Okay. L stands for liquid. And V stands for vapor. That is the medium which is present above the surface of the liquid. So this medium is what is vapor. Okay. So if I say TSV, it is the force that is existing at the surface, at the solid and the vapor interface. So where is the solid and vapor interface present? Observe, I'm going to explain it. So this is the solid and this is vapor and this is the interface. And due to the solid and the vapor interface, the particle O will experience a force in the upward direction. Similarly, SL stands for what? It is a solid liquid interface. So this is the solid and this is liquid. So the interface is here. So it will experience a pulling force in the downward direction. Similarly, you have liquid vapor, right? You have liquid vapor interface. So this is the boundary for the liquid and the vapor. So there will be a force acting here in this direction, which is called as the surface tension at the liquid vapor state interface. And FA stands for the adhesive force. Guys, is there any doubt till here?
No, sir.
Good. Okay. So let me read out the names. So surface tension of the liquid vapor interface is given as TSV. Similarly, surface tension for the solid vapor is given as TSV. For solid liquid is given as TSL, and the adhesive force is given as FA, which is going to exist between the molecules of the liquid and the container. Okay. So now comes an important question. If I take this diagram separately, so if I take this diagram separately, observe. Now, what can I do to this surface? If you observe, on point O, there is a force acting in upward direction, which is TSV. There is a force acting to the left, which is FA. There is a force acting in the downward direction, which is TSL. And TLV can be resolved into two components. What are the two components? One is TLV cos theta and TLV sin theta, where this is TLV making an angle theta. Guys, are you able to understand that? So this is the particle O. For O to be at equilibrium. Okay, for O to be at equilibrium, what are all the forces that are supposed to be balanced? TSV, that is this force, should be balanced by what all forces? Should be equal
TLV
to
sin theta plus TSL.
very good. TLV sin theta plus TSL. Similarly, TLV cos theta should be balanced by the adhesive force. Right? Sorry, guys, able to understand this? So these are the two mathematical expressions which we are going to get for the case of the liquid to get the molecule at O to get balanced. That is for equilibrium. Okay, FA must be equal to TSV cos theta, and TSV should be equal to TSL plus TLV cos theta. So from this, if you try to find what is the value of cos theta from this, 1 minute. Sorry. There is a mistake, guys. Can you correct it? I'll show you where is the mistake also. So what is the mistake I
Sin
did?
theta and cos
Sin
theta is
theta
interchange.
interchange.
Sin and yes, that's the mistake I did. So TLV cos theta, and this will be TLV sin theta. Okay. Now we can write TLV sin theta is equal to FL, and this will be cos theta. So from this, what is the value of cos theta? It is TSV minus TSL divided by TLV. Okay. So this is the value of cos theta. So make a note of this expression. There are some important conclusions we are going to draw from this. Where theta is what? Theta is the angle of contact. Done?
Yes, sir.
Okay. Now see. So what are all the possible values of theta? Theta can be acute. So if it is acute, then cos theta, is it positive or negative? Acute
Positive.
means what? It is positive because it belongs to first quadrant. If theta is obtuse, means it belongs to second quadrant. Then cos theta is negative. Theta is equal to 90 degrees. Implies cos theta is equal to 0. Okay. So from this, if I take acute into consideration, when cos theta is positive, then can I say TSV should be greater than TSL? Because cos theta is dependent on the difference of these two values. So TSV minus TSL should be greater than 0. So TSV should obviously be greater than TSL. Okay, this is when we have concave meniscus. Similarly, for obtuse, cos theta is less than 0. So TSV should be less than TSL, and it will have a convex meniscus. And when theta is equal to 90 degrees, then cos theta will be 0. It will have a plane surface. Okay. So listen. Okay. So since you have this notes already, you can go through this content later. You will understand. Are you done? Done, guys?
Done, sir.
Okay. So with that, the angle of contact and the shape of the liquid meniscus is over. Next concept is going to be capillarity. Okay. So let me explain what this capillary actually means. Okay. So listen. Suppose you have a container. in which I've taken a liquid. I'm not concerned about what kind of liquid I've taken as of now. Okay, since you would have seen this in real time, I'm just telling you. Again, we'll go to this concept only. Let's say you're going to a restaurant and you're ordering for a Coke and they bring it in a glass. Okay, so Coke majorly contains water, right? When you immerse a straw into it, okay, when you immerse a straw into it, I have an important question. Do you think the water level will still be here inside the straw, or it would have got slightly raised?
Raise, sir.
It would have got slightly raised, right? Are you guys able to understand?
Yes, sir.
Okay, so if you look at the size of the straw, it is very, very thin actually, compared to the size of the glass in which the cool drink is brought. The straw which you're using is thin, right? So the name capillarity actually has this meaning. Capilla means hair. A tube of very fine bore is called a capillary tube. So in this case, what you can say is the straw can be called as a capillary tube. See, straw is the term which we use generally. Capillary tube is a physics term. That's it. For you to understand, I'm just putting that term. So the liquid would have got raised. In a similar context, what will happen is if you have mercury in a glass, okay, and you put the straw into it, you can observe that the level of mercury inside the straw would have got dropped actually. That is a property it exhibits. Okay, why it is happening, all those things are different story. But if you observe, two important factors that we can observe is water and mercury. You can ask me why we are taking example of water and mercury, because water has an acute angle and mercury has an obtuse angle of contact. So again, we are going to take these two liquids into consideration and observe. So listen to this. When a capillary tube of glass open at both the ends is dipped in a liquid, okay, which wets its walls. So example of a liquid which can wet the wall is what? Water or alcohol. Okay. Then the liquid will rise in the tube. But when the capillary tube is dipped in a liquid which does not wet its wall, example is mercury, then the level of liquid in it will get dipped. It will get depressed. Okay. So the phenomenon that you're able to observe here, you're able to see the rise and the fall, right? The phenomenon of rise or fall of a liquid in a capillary tube in comparison to its surrounding is called capillarity. Okay, this is the phenomenon. The phenomenon is called as capillarity. That's what the topic is. Are you clear till this point? Okay, I've just explained what is the phenomenon. I'll tell you other examples of where this is applicable. Are you guys able to understand this?
Yes, sir.
Right? Okay. So this is the first phenomenon that is observed when we use a capillary tube. Now I'll ask you some more questions, guys. Tell me, okay? See, let's say you're writing on a paper right now. You're making a notes of the lecture. So when you're writing on a paper, there are different qualities of paper. Have you ever seen a low quality paper?
Yes,
Okay,
sir.
I'll ask you a question like this. Have you ever done this activity? Like you take a paper, you just place your pen at one point, especially ink pen, or you can think of a gel pen. When you place it at a point, if it is a low quality paper, have you ever seen that the ink will get bloated?
Yes, sir.
You have done it, right? So how is it actually able to happen? You're placing the pen at this point. See, the dot which I'm putting is the place where I'm placing the pen. But after some time, if you see, you can see that the ink is flowing through the pores and you can find a patch like this. Okay. So this is a phenomenon called as capillary action. Okay, this is one such examples of real-time basis. Similarly, you have a cloth. Okay, let's say you're sitting on a dining table, you're eating. Let's say there is some cloth beside you. So when water spills on it, what will generally happen? Will it be only at one place, or will it slightly start spreading to the other parts? It will actually start slightly spreading depending on the material of the cloth. Similarly, the other examples that are given here is, see, one I explained already. Blotting paper soaks ink by capillary action. The pores of the blotting paper act as capillaries. Capillaries are those tubes. Okay. Similarly, when you take oil, like when you light a lamp, right, you would have observed these during these Diwali times and all. What they do, they pour oil, and if you immerse the wick into it, the thread-like structure into it, what will happen is you can actually see the ink will flow from the sorry, not the ink. The oil will flow from the inner part to the outer edge. You can see that kind of a phenomenon. That is also happening due to the capillaries. Similarly, when you use towels made of coarse cloth for drying our skin after taking bath, when you take the cloth and touch it at the wet part, you can observe that water will be disappeared from there because the towel will start observing it due to the capillary action. Are you able to understand? So these are all some real-time examples of these capillary actions. And this phenomenon is what is called as capillarity. Guys, am I clear? Yes or no? Okay. So what we are going to, actually this is, the Ascent formula is the one which will actually use it in the lab. Okay. This big formula that we have derived is actually used in the lab. And we are going to see the derivation of it, which is based on the concept of capillary action only. Okay. So mark it as important and practice it. What we are going to do is we are going to calculate the height through which the liquid is actually going to rise. I told you, right, when you immerse a straw, the liquid is going to rise. Our interest of study will be to what height it is going to rise. Like when you use different liquids, how do you find the height to which they are going to rise? So derive an expression for the rise of liquid in a capillary tube and show that the height of the liquid column supported is inversely proportional to the radius of the tube. Means more is the radius, lesser will be the height. Right? So that's what we need to show. And the formula that we are going to derive is called as ascent formula because the liquid is rising. It's not descent formula. Okay. So we are trying to derive it for liquids which forms a concave meniscus. Concentrate. Okay. Concentrate. So consider a capillary tube of radius r. So there is a capillary tube of radius r which is dipped in a liquid of surface tension sigma and density rho. So this is the liquid which has surface tension T and the density rho. Suppose the liquid wets the sides of the tube. Okay, then it is going to form a concave meniscus at the top. So the shape of the meniscus of water will be nearly spherical if the capillary tube is sufficiently narrow pore tube. So here we are doing a small approximation. Observe what it is. If the size of the tube is very small, this is the important point. If the size of the tube is very small, that is, if it is a sufficiently narrow bore, then we can assume that this meniscus that is formed is not going to look like a parabola. Rather, it will be a part of the sphere. That is, if you take this portion only and draw it separately, then what we can say is this parabolic path, the parabolic shape actually, which you are able to see here, can be approximated to a sphere. Means it is going to be a part of the sphere which is actually not existing. Okay. So the center of the spherical part will be here somewhere over here. Let me call this as the center of the spherical part. And there are two R's used, one small r and capital R. Don't get confused between both. Small r is the radius of the capillary tube. capital R is the radius of the meniscus. Please make a note of it. Small r is the radius of the capillary tube and capital R is the radius of the concave meniscus. Done?
Could you repeat what's the last bigger?
Capital R is the radius of the meniscus. See, capital R is the radius of the spherical part. Smaller is the radius of the tube.
Okay, sir.
Got it? So, since it forms a concave meniscus, how will the angle of contact here be? The angle of contact will be theta, which is going to be acute again. Is this point clear, guys?
Yes, sir.
Now listen. So, since I'm taking it to be a spherical part, okay, this meniscus has how many free surfaces? This boundary has how many free surfaces? Free surface means the boundary should be exposed only to air medium, not the liquid medium. So here you have liquid. Okay. If I take it as water, this part is liquid. Okay. And here you have vapor. So here it is liquid. Now tell me how many free surfaces does it have, guys? What is so tough? I asked a basic
One, sir.
question. How many? It has only one. Okay. So when you talk about a sphere, we discussed two important concepts yesterday. What were they? One is excess pressure inside a soap bubble and excess pressure inside a water drop, right? So out of the soap bubble and the water drop, which one has only one free surface?
Water drops.
So can I say here the meniscus is behaving similar to a water drop? Right? Can I say that the meniscus is behaving similar to a water drop? That is the case. If I say the pressure inside is PA and the pressure outside is PB, okay, those are the 2 points A and B, then what is PA minus PB called as? PA minus PB is what is called as excess pressure. Am I clear? So PA minus PB is called as the excess pressure. Wait. There is too much information here. I'll take a separate page and I'll show you. But if there is any doubt, get it clarified. Now see. If I take a point here as PA and a point here as PB, then PA minus PB can be called as excess pressure. And what is the value of excess pressure? It is 2T divided by R. Here, if you observe, I didn't write small r because 2T by R, there R stands for what? The radius of the drop. So here the radius of the sphere is capital R. Are you guys able to understand why I wrote only 2t by r? Because there is only one free surface. Had there been two free surfaces, I would have written it as 4p by r. So if I call PA as atmospheric pressure, then what will be the value of PB? PB will be PA minus 2T divided by R. From this, I've rearranged the equation. Let me call this as equation number 1. Guys, am I clear? I'm repeating it. This derivation is important. So PB is equal to PA minus 2T by R. That is what is written here. As the pressure is greater on the concave side of the liquid surface, so the excess pressure at point A just above the meniscus compared to point B is 2T by R, where R is the radius of curvature of the liquid meniscus. Does this make sense?
Could you repeat this point again?
Which one? This one, 2T by R.
Yes, sir.
That's what I wrote here. No, see. This is the concave side. Now tell me, out of PA and PB, which side will have more pressure?
PA, sir.
Yes, PA, right? So if PA is having more pressure, then what do you mean by excess pressure? Excess means what? PA is absolute pressure. Absolute means it's the exact value. PB is absolute pressure. But PA minus PB is what is called as small p, which is excess pressure. So excess means how more or less. In fact, we are going to say how more a particular value is compared to something else. If I say you have excess money, means you have more than what is required. Are you able to understand? So PA and PB, the difference of those two is what is called as excess pressure. Since this meniscus has only one free surface, we derived a concept of excess pressure inside a liquid drop yesterday. What was it? It was 2T divided by R. And that's what I wrote here. Why did I write 2T by R? Is because there is only one free surface here. Okay. So since, see, this dotted part is actually not existing. It's not there. So the liquid is exposed to the atmosphere. So the pressure above the liquid column is PA, which is called as the atmospheric pressure. And pressure inside the liquid, if I call it as PB, then PA minus PB is what I'm calling it as 2T by R. So if PA I call it as atmospheric pressure, then what will be the value of PB? PB will go to the other side. 2T by R will come to the other side. So what will be that? What will that value be? It will be PA minus 2T by R. That's what I wrote here. Are you clear?
Yes, sir.
Yeah. So that's the point they have given. I'm just reading out what they have given. So listen. Pressure at point A just above the meniscus compared to point B just below the meniscus is going to be 2T divided by R. Okay. Where capital R is what you need to write because that is the radius of the meniscus. If I take theta as the angle of contact, okay, if I take this triangle, if I take theta as the angle of contact, look at the way I'm going to shift the angle. So if this is taken as theta, then how much will this angle be? Remember, this is tangent. This is normal. It is 90, right? So it is 90 means then how much will this angle be?
90
This
minus
will be
theta.
90 minus theta. 90 minus theta. From 90 minus theta is gone. This angle will be theta. Convinced? So the black angle will be theta. So in the triangle, if I take the right angle triangle theta, capital R, small r, these are the two important sides for me. Okay. So what is the trigonometric ratio I can think which gives me the relation between adjacent and hypotenuse?
Cos.
We can either think of cos or secant, but we will go with the basic one, cos theta, which is small r divided by capital R. Right? So that is the second point. Okay. So from this, what we can do is we can find out the value of capital R, because capital R is not an information that we can find easily. It is not easy for us to find the radius of the spherical drop because it's not a complete sphere. It's just a part of something. Whereas it is easy for us to find the value of smaller. So whenever you're deriving a formula, right, your formula should contain all the parameters which are easy to find it on a real-time basis. So what we will do here is we will write capital R in terms of small r. 1 minute. This is equation number 2. So if I write excess pressure, that is 2t divided by r, can I write this as 2t divided by r divided by cos theta also? So this is going to be 2t cos theta divided by r. Okay. Next. So listen, due to this excess pressure P, the liquid rises in the capillary tube to a height h when the hydrostatic pressure exerted by the liquid column becomes equal to the excess pressure. Okay. So what they are trying to say is, due to this excess pressure, the liquid rises in the capillary tube, let's say to a height h. When the hydrostatic pressure exerted by the liquid column becomes equal to the excess pressure, we can attain equilibrium. What they are trying to say is, see, the liquid would have slowly rise. No? It is not like it is a single process. Like as soon as you immerse, it is going to go to this height. It takes some time for the liquid from here, liquid at the surface, to travel to this height h. And why is it happening? What is the reason behind? What is the reason behind the liquid to raise? There should be some pressure, right? So it is the excess pressure that is present inside, excess pressure that is present causing the rise to the liquid. Okay, when the excess pressure becomes equal to the hydrostatic pressure, if you recollect the concept, pressure due to the liquid column, then the height of the pressure due to the height of the liquid column is going to give us rho gh. Do you guys remember this formula? So this is the expression for excess pressure. H rho g is the expression for pressure due to depth. When these two parameters become equal, the further rise of the liquid is going to stop. Okay, why we need to write this is because we are concerned about what is the maximum height to which the liquid can get raised. So when I write P is equal to rho gh, that is when the excess pressure is equal to rho gh, that is 2t cos theta divided by r is equal to rho gh, where rho is the density of the liquid, g is the acceleration due to gravity, and h is the height to which the liquid gets raised. So h will be equal to 2t cos theta divided by r rho into g. And this formula is what is called as ascent formula. Clear, guys?
Clear, sir. This is for a concave meniscus only, sir, or will it be the same for convex also?
Convex, we are not concerned. Convex, it will be descent. Because we don't use convex. Mainly, this formula is derived for the lab purpose. When you do this experiment in the lab, you use only liquids which will tend to raise.
Okay, sir.
Okay. If at all you have lab manual, if you're writing, you can check this experiment. It will be under the concept of surface tension. Is that clear, guys?
Yes, sir.
Good. So, with this, the chapter has come to an end. This is a very, very big chapter. Okay. You need to work more on this, and this chapter is mainly important for other exams. For CBSE part, yes, of course, you need to concentrate on all the derivations and all those stuffs. Okay. So I suggest you guys to start reading. If you have any doubts, you can approach me personally. So that's the end. So in tomorrow's class, I'll be starting the next chapter, that is 11th chapter, which is based on heat. That's called as thermal properties of matter. So if you observe, the first two chapters that we read in this chapter, in this second volume is, what was the ninth chapter? It's called as mechanical properties of solids. And this chapter was called as mechanical properties of fluids. The next one we are going to see is mechanical properties of materials. Here we are not going to be concerned about whether it is a solid or liquid. For everything we will discuss as a package. Okay. From here again the chapters are small. We can complete it soon. So by the end of December or by the first week of Jan, your physics syllabus will get over. So I'm repeating it again. Keep preparing continuously so that your final exams become easy for you. You're not sure how they are going to ask, so start preparing. Okay. So any other doubt from this chapter? Okay, I'm assuming no doubt. Just wait for a minute.